Yes, so I'm Jacob Luhn. I'm a NASA postdoctoral fellow at JPL, and I just want to say thank you to the organizers and Shelley for letting me give this talk virtually. I was really looking forward to being there in person this week, but my water heater had different plans, so it's been a weird week for me. I'm excited to take a break from packing up all of my belongings to talk about science. And so this is a recent program I've been running to capture short timescale variability in radial velocity time series with the Keck Planet Finder. And I just want to start with the justification for extreme precision radial velocity technique as the only method potentially capable of detecting and measuring the masses of Earth analogs orbiting solar type stars from the ground. And this is especially relevant in the lead up to the Habitable Worlds Observatory, as these EPRV surveys are expected to find the most promising Earth-like planets. However, the biggest challenge that we face now in reaching the necessary 10 centimeter per second level precision is not instruments themselves, but really the stars, so stellar variability. And so I'm showing here the various sources of RV variability by their amplitude on the y-axis and timescale on the x-axis, with the RV signals from Earth and Jupiter shown with their respective cartoons. But I want to look at this a slightly different way. So here are some observations for a simulated extreme precision radial velocity survey over a 5-year span with synthetic radial velocities from only stellar sources. And on this timescale, activity cycle is pretty easy to pick out as kind of this long-term trend. And on top of that, there's monthly rotation, which when we zoom in, we can see is pretty well traced by our observations. Only appearing as wiggles here until we zoom in again are night to night variations from supergranulation, which are hardly sampled at all. And then within a night, RVs are dominated by granulation and oscillation, which are even more poorly sampled. And so this highlights a key challenge that we face when we're trying to characterize, diagnose, and mitigate these sources of variability in other stars. And especially on these shortest timescales, we really require dedicated and targeted observations if we want to study them in detail. So I'm going to be focusing today on this bottom box, this shortest timescale sources of stellar variability, P modes, and granulation. And so if you're not familiar, P mode oscillations are pressure-driven waves that are excited by convection and travel throughout the interior of a star. And for the sun, this occurs with a characteristic frequency of about 5.5 minutes. And to an astroseismologist, the statistical properties of these oscillations are related to a star's physical properties like mass, radius, and age. And so we often think about this in Fourier space as the power spectral density shown on the left, but we can also model this in covariance space using equivalent Gaussian process kernels for simple harmonic oscillators. And this is because, unlike astroseismologists, we don't particularly care about how the star behaves on average. We want to be able to know what the star is doing during or immediately surrounding our observations. And that's where Gaussian processes are extremely powerful. And so what we're hoping is that we can take advantage of our expectation that while planets induce a pure Doppler shift, stellar variability will induce complicated shape changes. And this is what you can see here in these cartoon cross-correlation functions, or CCFs. This is just an average stellar line profile. And this is how we derive the RVs for stars. And at the bottom here, I've listed a few examples of methods or techniques that try to leverage this expectation of shape versus shift changes in finding planets. But the question is, are these expectations realistic? And to what degree do oscillations and granulation induce shape changes that are actually distinguishable by these techniques? And so with EPRV instruments, we're now poised to diagnose the spectral effects with incredible precision. And so as a starting point, we've turned to an extreme. This is an evolved subgiant star with oscillations that span several meters per second here over a 90-minute long cycle. And we resolve these oscillations with a single night using NUID, which is an EPRV spectrographic kit peak. And with this time series, we can break this up into horizontal bins of similar velocities and compute the residuals between the CCF of the observations within each bin compared to the mean CCF for all of our observations. And so you can see on the right that these CCF residuals in color for each bin look nearly identical to the residuals that you would get from a pure shift, so a Doppler shift. And those are shown in the dashed line in each of those plots. And so we can do a similar investigation directly on the CCF, and we can compute the bisector velocity for individual portions of the CCF. And then when we view those time series for each of these bands of the CCF, we maybe see this a little more clearly. Each band's velocities are in sync, implying that the whole CCF is moving together. However, you may notice, if you have a keen eye, a bit of a gradient here, indicating that there's a subtle amplitude difference as you move either up or down in the CCF. And so we can measure that amplitude difference and see that indeed the oscillations at the core, so at the bottom of the CCF or to the left in panel C here, these oscillation amplitudes are larger than the velocities drawn from the center, or from the wings of the CCF, sorry. And so what we're really seeing here is that the CCF is tracing the density profile of the stellar atmosphere with larger velocities higher in the atmosphere where it's less dense. And so this is a really nice result for a subgiant star. And the next step is to confirm this with other stars. And so that's led to this program that I've been running to get more of these single night stares of stars across the HR diagram. And so we've been continuing to use NUID to target evolved stars with larger amplitudes and longer time scales. These are towards the top of this HR diagram. But the real advantage then comes from the Keck Planet Finder, which has a fast readout mode to get extremely high cadence observations at equally high SNR for a fraction of the exposure time. And this is what really allows us to resolve oscillations in dwarfs. And in particular, we've been highlighting or targeting high priority HWO candidate targets. And so in total, we have 11 high cadence sequences, of which 6 have more than 6 hour time baseline on their night. And here's what those time series look like. And so the top 3 are NUID RVs, so more evolved stars, and the bottom 3 are from KPF, so dwarfs. I just want to take an extra second here and marvel at the precision and cadence that we're able to achieve with these EPRV spectrographs and get such cleanly resolved oscillations in the time domain. And in some cases here are Gaussian process fits. Those are the gray lines in these plots. It's essentially beads on a wire here. But back to the analysis, we can repeat what we did for our case study, which is the top star on the right, HD 142091. We can repeat that CCF velocity analysis for all of the stars in our sample to see how these oscillation amplitudes vary along the CCF bisector. So that's what I'm showing in this rather busy grid of plots. And so they're ordered from left to right and top to bottom, from most evolved to least evolved. So our case study, HD 142091 in the top left, and K-dwarf SIGDRA in the bottom right. So also NUID targets are highlighted in the orange boxes and KPF in blue. And to complicate things even more, I've also included 2 sample days of solar data from when both NUID and KPF were observing the sun. And so we notice a few things here. In general, we see the same or similar trend for all of our targets, and that is larger oscillations in the core of the CCF compared to the wings. There's a possible hint of a flattening or maybe even a reversal for these K-dwarfs, but I'll note that these 2 are really testing KPF's limits. It's a challenging observation to make, and so the uncertainties there are much larger. But the big takeaway here is that for all of these stars, cool, thanks, the CCF only exhibits very subtle differences across the CCF, behaving more like pure shifts rather than a shape change. And this challenges the assumption of a lot of current mitigation techniques. And so we can't expect existing techniques to work on P-mode oscillation. So what about granulation? And that's our next step. So with these KPF time series of dwarfs, we have long enough time baseline within a night to resolve variability, not just from oscillations, but also granulation. And so we can perform these same types of analyses and really diagnose how granulation affects the spectral profile. And so with both of these, granulation and oscillations, if mitigation techniques, the existing ones, aren't sufficient, we can use these high SNR time series to search for new diagnostics and develop specialized mitigation techniques. And just circling back to this plot, I think it's quite likely that each of these sources will require their own mitigation strategies at the spectral level if we want to push down to the 10 centimeter per second and level and below to find Earth twins. And it's even possible that each star will require its own tailored variant of each of these techniques. For example, mitigating granulation may need us to isolate a different population of absorption lines in Tau Ceti than, say, in Sigdra. And so this growing sample of stars then serves two purposes. First, to test how generalizable or tailored our mitigation strategies need to be. And second, just to build the foundation of an HWO target list where every star has a complete picture of stellar variability down to the shortest timescales. And so I'll leave you with those thoughts and put up a summary slide of some of these initial science takeaways and next steps that I talked about, and let you peruse those while I open it up to questions. Thanks.